Hi, I'm Tanishan. I'm leader from Group 12. My group members, Kersing, Jingshen, Sam E, and I will do this video presentation for TCN project. Okay, so for this video presentation, we will show you the implementation and the budget, and following addressing table. And we also will show you the network design, the physical network design and logical network design. And then we will show you how we configure the network, and following is the conclusion. Our project is composed of several stages, including planning, implementations, testing, and documentation. At the planning stage, we analyze the project requirements and start the topologies design. After the interim report submission, we start finalizing and configuring our network design. We have done the error checking after the implementation, and all the processes and steps are documented. Finally, our report and presentation will be done before the submission date in week 13 and week 14. Okay, this is our budget. So you can see the table here. We have buy some software and hardware requirement like PC, server, router, switch, monitor, accessing point, file server, DNS server, web server, and the cabling and socket components. So for the cabling, we have buy the internet cable and serial cable. So our total is around 262,000 and above lah. So, and then for the man hours requirement, our project will hire one network architect to plan, design, and build the network topology that meets our criteria. Besides, around 6 senior network engineers will be hired also to cooperate with the network architect to design and implement functional company networks. So for networks architects, the salary will be 8,000 per month, while for senior network engineers, their salary will be 6,000 per month.
For our addressing scheme, we subnet this into 64 network using a logic that match our router roles. For the core router, we assign the lower subnet 10 for lab 1, 20 for lab 2, and 30 for classroom. These are all student-focused area. For the internal router, we assign the specific function subnet 40 for administration office, 16 for server room and system administrator room, and 17 for the wireless network. This logical pattern makes network management and troubleshooting efficient. If we see an IP with 16, we immediately know it belongs to the server room on the internal server. All student PCs and end device receive their IPs automatically via DHCP. So, these structured addressing schemes ensure our network is scalable, organized, and easy to troubleshoot. Now, I will talk about the topology. This slide shows the physical topology of our university campus network based on the floor plan. Our designs use a star topology where all network connections from different rooms cover to one central location. In the diagram, the central point in the main rack located in the system administration office, shown by the white server icon. From the top row, we can see classroom 1 to 7, each containing a tutor PC connected back to the core network through Ethernet cabling. On the right side, we have lab 1 and lab 2, which contain many student computers. These labs are physically connected using wires, Ethernet to ensure stable and high-speed access. On the left side, the administration office also connected back to the same central hub, allowing staff to access internal resources. The server rooms is positioned near the center for better security and efficient cable management. Overall, this physical layout provides centralized control, easier troubleshooting, and reliable connectivity across the campus. Moving to the logical topology, we distribute the IPv6 subnet based on the router physical role. In our logical design, each switch represents a distinct broadcast domain and corresponds to a specific IPv6 subnet. For instance, the switch connecting to the core router Gigabit Ethernet 0/0 interface is logically assigned the 10/64 subnet. Any device plugged into this switch automatically receives an IP from this specific range via DHCP v6. On the core router, subnet 10 and 20 are assigned to the student lab 1 and lab 2. So, subnet 13 is assigned to the classroom. On the internal router, subnet 14 is the administration office, subnet 17 is for the wireless network, and subnet 16 is the most critical subnet. It hosts the server room and the system administrator office. As mentioned, the system administrator has full privilege. To ensure connectivity, between the student zone and the server zone internal, we configure OSPF v3. This dynamic routing protocol allows students in Lab 1 to access the web server on internal automatically. For the internet connection, we use a default static route pointing toward the ISP router, ensuring that all of authorized traffic has a path to the internet.
Now I will continue with the configuration part of our project. First, we configure the basic router settings. We set the host name to identify the router in the network, and then we enable the IPv6 unit cast routing so that the router can forward traffic between different networks. After that, we assign the IPv6 addresses to the interfaces and activated them using the no shutdown command. This prepares the router for communication with other devices. Next is the cloud configuration part. First, 00 inside the packet tracer cloud connects to the core router. This provides the one link between our internal campus network and the ISP network. Then, 01 connects the cloud to the ISP router. This represents the ISP side of the one connection and allows traffic to reach external networks. Lastly, we configured frame relay inside the cloud. Frame relay maps 00 and 01 together. This allows packet entering one interface to be forwarded to the other. The one communication would not work properly without this mapping. For the routing, we implemented OSPF v3, which support the IPv6. We created an OSPF process and configured a router ID to uniquely identify each router. Then we enable the OSPF on every interface and assign them to area 0. With dynamic routing, routers automatically exchange the routing information and update their routing tables. This is more scalable and efficient compared to the manual static routing. To simplify the client configuration, we implemented DHCP v6. We created a DHCP pool that provides the IPv6 address range and the DNS server address. This allows clients to automatically obtain the network information without manual configuration. On the interface, we enable the other config flag and link it to the DHCP server. As a result, devices in this subnet can connect to the network immediately. Besides the dynamic routing, we also configure static routes. The default route forwards all unknown traffic to the ISP, which provides internet access. We also added specific routes to ensure traffic reached the correct internal subnet. Static routing gives us a better control, and it is useful for smaller or predictable networks. Besides network devices, we also configured 3 servers to provide the network services. First is the DNS server. We assign a static IPv6 address and enable the DNS service to translate domain names into the IPv6 addresses. Next is the web server. We enable HTTP and HTTPS services to host the university website so the user can access it through a browser. Lastly is the file server. We enable the FTP service and created user accounts to allow file uploading and downloading. These servers provide essential services for the whole network. Lastly, we verify the network connectivity. First, we use the show IPv6 interface brief to confirm that all the interfaces are showing up. Then, we check the routing table using show IPv6 route to ensure the routes were learned correctly. We tested the connectivity by pinging the DNS server address. The successful replies shows that our routers, one connection, routing, and servers are all working properly.
Okay, let me add that besides that what was mentioned earlier, we also have configured the SCL. So this router configuration block web browsing to the internet. It creates a filter that denies both HTTP and HTTPS traffic while allowing all other internet traffic and network diagonals. So the filter is applied to 2 outgoing interfaces, preventing users from accessing websites through those connections while keeping others online services working normally, especially for the ISP.
Now I would like to demo the connectivity of different devices across the network. First, we ping the PC from Lab 1 to Lab 2. Now I choose PC 23 in Lab 2 and go to command prompt and type ipconfig to get the IPv6 address of PC 23. So I copy it. Then select PC 22 in Lab 1 and go to command prompt and ping. Then it is successfully 0% loss. Next, we ping from class to PC to Lab 1. Same step, we first get the IP address from the PC in lab 1, for example PC 12, and copy the IP address. Then we go to PC in class and go to command prompt and ping. And it is successfully 0% loss. Next, we ping from System Administrator Office to Administration Office. Same step, we first select any PC in Administration Office and get the IP address. Then copy the IPv6 address and go to any PC in System Administrator Office and ping. So it is successful, 0% loss. And lastly, we ping from the laptop in wireless network to PC in lab 2. So I select PC 38 and get the IP address and copy it and go to laptop in wireless network, command prompt. And it is successful as well, 0% loss. That's all from connectivity. Our group has completed the security implementation for all routers and switches in the topology. We use the same password for all devices to ensure consistency. Now I would like to present the core router. When we access the core router through the CLI, we first need to enter the console password. After that, when we type the enable command to enter privilege mode, the router requires another password, which is the enable secret. But for our system, we use the same password. Yeah. Next is class switch. Accessing the CLI requires a password. And entering enable mode also requires a password. That's all for security.
In summary, this project successfully designed and deployed a comprehensive IPv6 enabled campus network for an IT university, meeting functional requirements across all departments and services. Careful planning, organized architecture, and detailed configuration ensure reliable connectivity, logical segmentation, and centralized management. The use of IPv6 addressing supports long-term sustainability and efficient address management, while a hierarchical network design enhances scalability and simplifies future expansion. Implementation of several services, DHCP-v6 and routing protocols demonstrates the network's ability to serve both wire and wireless users effectively. Verification confirms that all devices and subnets are properly connected and functioning as intended. That's all for our presentation. Thank you.